This relationship is equivalent to a 50% proportional band, since 1/2 times 100% equals 50%. With a narrow proportional band, control action is rapid, and the value of the controlled variable stays closer to set point. However, decreasing a proportional band setting increases the amount of cycling, which can overwork system components. Now, the signals on this graph show a proportional band that's greater than 100%. This type of proportional band is called a wide proportional band. With a wide proportional band, a large change in input to the controller produces a smaller change in output. The proportional band for this example is 200%. Since the output signal changes less than the input signal, a wide proportional band can minimize the amount of cycling in a system. However, there's more offset with a wide proportional band. Some manufacturers use the term gain when describing a proportional control adjustment. Gain is the inverse of proportional band, and it's expressed as a quantity rather than as a percent value. For example, a 1 psi change in input that produces a 2 psi change in output represents a 50% proportional band. But since gain is the inverse of proportional band, the relationship between the change in input and output is reversed. So the gain in this example is 2. In this topic, we examined two-position control and proportional control, and we looked at how those control modes work in an automatic control system. Now let's try some practice questions. Now, in a two-position control system, a certain amount of change can occur in the process without causing a control system response. This amount of change is called the dead zone. The input and output signals on this graph represent a proportional control system's response to a continual disturbance. Proportional band is the amount of output change, or delta output, in relation to a given amount of input change, or delta input. Not all control modes can return a controlled variable to set point after a process disturbance. However, reset control is designed to adjust the output of a proportional controller to help eliminate offset and restore original process conditions. Reset action responds to a controlled variable's deviation from set point by increasing or repeating the amount of proportional control until the variable returns to set point. Reset control doesn't exist without proportional control. In fact, it's actually proportional plus reset control, since it adds an additional corrective action to the proportional action. Also, reset control is sometimes called Proportional+Integral, or PI control, because it's based on a mathematical function called integration. In any case, it's easier to understand how reset control works by looking at an example. In this arrangement, an automatic control system is used to maintain the level of water in a tank. The input signal from the transmitter to the controller represents the level of water. The output from the controller adjusts a control valve in the supply line to the tank. If a continual disturbance causes a decrease in the flow of water from the tank, the level in the tank rises, and the input signal to the controller changes to reflect the higher level. How do you suppose the controller responds to the change in level? The controller responds by signaling the control valve to close down. This reduces the flow of water to the tank and allows the level in the tank to gradually return to set point. We can get a better idea of how the system responded to the disturbance if we plot the input and output signals on a graph. We'll include a time scale on the graph to see more clearly how the control action works. During the first minute, the increase in water level caused the input signal to the controller to increase from 9 psi to 11 psi, which is a change of 2 psi. During the same 1-minute interval, a proportional-only controller with a 100% proportional band would have produced an output signal that matched the input signal. But the output signal from this controller includes proportional action plus reset action. And it increased to 13 psi, a change of 4 psi. What this means is that the reset part of the control action increased or repeated the 2 psi proportional action one time in 1 minute. This is sometimes described as 1 minute per repeat, or 1 MPR. As the level of water in the tank dropped, both signals decreased, then fluctuated briefly before returning to steady state. That's because the value of the controlled variable, represented by the input signal, returned to its original set point of 9 psi. In our example, a reset control action of 1 minute per repeat was able to return the controlled variable to set point. Often the amount of reset in a system can be adjusted. However, a reset that's too fast can cause a controller to overcorrect and cause the process variable to cycle out of control. In those cases, a slower reset may be needed. Rate control is a control feature that responds to the speed at which a variable deviates from set point. The faster the variable changes, the greater the amount of rate control action. Rate control is normally combined with proportional control, so it's often called proportional plus rate control. Also, it's sometimes called proportional plus derivative, or PD control. In any case, when a process disturbance causes the input signal to a rate controller to change, the controller measures the speed or rate at which the input is changing and produces an instant boost to the proportional output signal. In effect, this action tries to stop changes in the input as soon as they're detected. To get a better understanding of rate control, we'll use this automatic level control system in which rate control has been added to a proportional controller. We'll say that a continual disturbance causes a decrease in the flow of water from the tank, which in turn causes the level in the tank to rise. If we look at a graph of the control signals from the process, we see that the rate controller responds to the disturbance by producing an immediate boost in output. This boost minimizes the water level's deviation from set point. Then, a combination of rate control and proportional control stops the water level from changing and brings it down almost to set point. However, because rate control responds only during changes in the input, and because proportional control only provides a proportional output, there may be some offset in the process variable. In other words, as long as the level is at steady state, even with offset, the rate controller will not provide a correcting output.